Welcome to this afternoon session. The first speaker is Mark Mezei from Oxford, and he will talk about quantum mechanics of old black holes.
Thank you very much. I would like to start by thanking the organizers for the opportunity to present this work here. The context of this talk is that there's been a renaissance in the last 10 years of Euclidean gravity methods, which were originally pioneered about 50 years ago. Then they provided a mesoscopic derivation of black hole entropy, but what I mean by mesoscopic is it's neither microscopic in the sense of string theory entropy counts, nor completely macroscopic, like thermodynamic arguments based on the laws of black hole mechanics. Euclidean methods were used to propose a wave function for our own universe, the no-boundary wave function of Hartle and Hawking, which was discussed in one of the parallel sessions extensively. But these Euclidean methods are plagued by some problems, several of them. For one thing, it's unclear what's the relation between Euclidean and Lorentzian approaches, so canonical quantum gravity. There were wormhole contributions, and there were endless debates about whether to include them or not. There's the conformal mode problem in higher dimensional gravity, and a few others. Nevertheless, in the holographic ADS-CFT context, the Euclidean methods have proven to be very useful. Lukowitz and Maldacena use these methods to provide the derivation, again, the Euclidean path integral derivation of the famous Ryuta-Kanayagi formula for the entanglement entropy of the boundary quantum field theory. And more recently, starting with the work of Schenker-Stanford and many important contributions afterwards, it was understood that wormholes, specific kind of wormholes, encode the spectral correlations of the dual quantum system that is expected to be chaotic, and hence these need to be taken into account. Of course, once we include them, they raise new puzzles, and people have been actively working on resolving those. And again, a mesoscopic resolution of the black hole information paradox was done, and we heard a very nice discussion in Kumar's talk of this and extensions. Okay, so one of the main focuses of my talk will be to connecting Euclidean approaches to a Hilbert space view, and this is completely standard in quantum field theory. So let's consider two-dimensional QFT on a sphere. We can cut open this path, this integral, along the equator, this blue equator, thereby obtaining a bra and a cat. So let's focus on this path integral. Let's fix the field configuration on this blue circle, phi of x, and then perform the path integral, thereby obtaining a wave functional evaluated on this field configuration phi. And then with these wave functions, we can start doing ordinary quantum mechanics. So let me just review how you do that. So of course you can insert local operators into the path integral, but let me instead insert the non-local operator, the exponentiated integral of this field phi on this circle. Okay? So we can compute its expectation value in two ways. The Euclidean way would be just to stuck this object into the Euclidean path integral and compute. But there's a Hilbert space way. We can take the product of bra and cat, form a probability distribution, and then evaluate again the one-point function, and these two agree. Okay? And these two descriptions, two viewpoints, have complementary advantages. The Euclidean approach is often useful because we can find saddle points. Depending on the question that we are asking, we may find different saddle points. And also we can access Lorentzian physics through analytic continuation. The Hilbert space view is useful because it makes unitarity manifest. It makes the probabilistic interpretation, like here, manifest. And it also encodes integer degeneracies of states, which is very hard to see in the Euclidean approach. So we can try to do the same thing with gravity, and to some extent we can do that. So we can consider the same Euclidean path integral, cut open the sphere. Now the geometry is fluctuating, so we have to be careful with specifying where we cut open. An elegant prescription would be to cut open on a geodesic, or in higher dimension, a minimal volume slice. And then we get a wave functional, which depends on the induced metric on this cutout, on this Cauchy slice that we cut open. We have to be careful, just like in any gauge theory, with diffeomorphism invariance. But we can insert diffeomorphism invariant operators and can compute both in the Euclidean and the Hilbert space way. But there's a problem. In gravity, it's not just the metric that's dynamical, but even the topology is. So we can encounter configurations where there is a wormhole connecting this bra and the cat. And it's unclear what to do with them. Should we cut them open? Do they describe a mixed state? And in Gorbenko's talk, there was a discussion of this. It may be that depending on the physical question we are asking, we're supposed to do different things. So the key point now is geometry is fluctuating. So even the question of how long this circle is a dynamical question. We can compute correlation functions of this length. And indeed, that's what I'm going to do in a related context. So I will, instead of providing a very abstract discussion, I will focus on an application while building a general formalism, which will be the volume of a black hole interior. And in a very simple model, this two-dimensional JT gravity that was already discussed at this conference. It's based on these two papers with a number of excellent collaborators. Okay? So there's an additional motive. So why do I care about the length or the volume of the black hole interior, which in two dimensions is the length? Why is this a particularly interesting question? So from my point of view, it's very interesting because there's been a very fruitful crosstalk between the quantum physics of black holes and the study of chaotic many-body quantum systems or quantum field theories. It featured also in this conference already. And so here I'm showing a Penrose diagram of an ADS black hole forming from collapse. So this is the boundary where the holographic field theory is imagined to live. And this is a Cauchy slice on which we prepare some disturbance, which then collapses into the middle of the black hole, forming a horizon. This is a singularity. Okay? So this process here, it's described by geometry. In the dual quantum system, this process is the process of equilibration, of thermalization in the dual quantum system. Now there's one striking feature of this space-time, geometric feature, whose dual we don't really understand satisfactorily, which is that the interior of the black hole, as measured by maximal volume slices anchored at different times on the boundary, is growing linearly in time. Okay, so these things, I mean, this is a Penrose diagram, so it doesn't capture lengths, but if you compute, believe me, it grows linearly in classical gravity. And it grows indefinitely. And so it's a nice geometric feature of the bulk. We would like to understand it from the boundary. And indeed, Susskind and collaborators have an appealing proposal for what this should be, although it's a bit vague proposal. So first, let's look at the blue curve. That's the volume. It's growing forever. Now, even if you consider somewhat complicated observables like entanglement entropy, it starts growing linearly but saturates very early on. So in quantum chaos, there are many time scales, and this is a somewhat early time when it saturates. So because of the failure of these somewhat medium complicated observables, Susskind and collaborators consider something more arcane, some computational complexity of the evolving wave function. The details are not clear. There was a nice talk by Caputa in this conference about Krylov complexity resembling this evolution. So from many body arguments or quantum field theory arguments, you expect that this kind of complexity should roughly evolve linearly until very, very late times, exponentially in the entropy. So in usual large n systems, it would be e to the n squared, so very, very long times. This is what we call the Heisenberg time in quantum mechanics. So this is the latest time at which any reasonable observable should stop evolving. The state becomes completely random for all intents and purposes. And so the proposal is that until then, this complexity should grow and then saturate at some exponentially large value. And so in the first paper, we asked whether there's a quantum gravitational effect for these old black holes, so we are going very late, that would also halt the growth of the volume and give an agreement between this orange curve and the blue curve. So in the next section of the talk, we will do a Euclidean gravity computation and indeed find agreement. And then I will present an alternate Hilbert space view, which is maybe a bit, contains more information, and then I will end with a summary. Okay, so we want to do quantum gravity. Quantum gravity is hard, so we will make 2 steps to simplify the problem. So gravity with matter is messy. Hartmann and Maldacena taught us how to do similar chaotic time evolution in pure gravity, and that would correspond to taking the eternal black hole and anchoring observables on both sides simultaneously. So you can see the maximal volume slices are simply, on this side, are roughly doubles of what I have here, but I eliminated matter. Okay, so that's good. Now, gravity becomes simpler as we go down in dimension. So we will go down to the lowest dimension where this question can still be asked, which is 2-dimensional dilaton gravity, JT gravity, which, as was emphasized, can be regarded both as a toy model but also as an effective field theory for near-extremal black holes. It's defined as a renormalizable path integral over all metrics and all dilatons, and consists of a topological term, chi is the Euler characteristic, and a dilaton gravity action. I won't be doing detailed computations in this theory, but I will flash some results. Okay, so as I said before, I would like to compute the length of the black hole interior, and I will do Euclidean computations. And you can reorganize the Euclidean computations as follows. So take a hyperbolic disk. This wiggly line is the ADS boundary. And then cut it open and have a geodesic stretching from this point to this point of length L. Now we get a bra and a ket wave function. From these parts, we stick in L and then evaluate. So this is a Euclidean calculation, but I'm reorganizing it in a way that makes it suggestive of Hilbert space interpretation. And okay, 2 things I didn't say is that the only gauge invariant observable of a geodesic in 1-dimensional, like a geodesic line, in 2-dimensional gravity is its length. So this wave function only depends on the length. And it also depends on the length of the asymptotic boundary, which we initially take to be beta over 2, where beta is the inverse temperature. But then we analytically continue. So I'm exhibiting the features I emphasized, that you can get Lorentzian physics out of Euclidean physics by analytic continuation. Okay, so this calculation was done by Zhenbin Yang. We know these wave functions explicitly, and so you can just do these integrals, and at some relatively late time, you get exactly linear growth. So I would like to emphasize this is not a classical result. This is all loop graviton fluctuations. Nevertheless, the linear growth is not corrected. So what we conclude from here, so we see the growth, but we don't see the saturation, that perturbative gravity is insensitive to the Heisenberg time, and so we need to include non-perturbative effects. Okay? And so that's what we did. As in my introduction, what you do is you include these kind of wormholes that connect the bra and the cat of the wave function. So you can see this L geodesic here, and the wiggly boundaries here and here, and then some complicated topology connecting the two. You can do these computations pretty explicitly, and at every genus, so in 2 dimensions, topology is characterized by genus. At every genus, you get a very similar formula to what we had before. So some L and then some quantity that wants to be a density matrix, right? So I can rewrite this as a trace of L with rho G. But we're doing a Euclidean calculation, and but if we try to interpret this in a Lorentzian manner, we encounter a puzzle. This rho G is not normalizable, so you cannot impose that the trace of this density matrix is 1. Okay? But this is... Oh, it's from... So this is a renormalized length, because we are going to asymptotic bound, so it's from minus infinity to plus infinity. But this is just an attempt at rewriting. This is still a completely legal Euclidean computation, and indeed you can follow it through and we will get the result. But this is a puzzle. How do we cut things open? How do we interpret this in a Hilbert space manner? Okay, so there's a long and beautiful and mathematically sophisticated story here that I'm suppressing. This genus expansion can be resummed in terms of a random matrix theory, as was shown by Sachenker Stanford, building on the mathematical work of Mirzakhani and Einard Oranten. Some of this was discussed in the Bohr's talk. And there's a final expression that we obtained for this length expectation value, which depends on spectral correlations, spectral 2-point functions of the dual quantum systems. And so indeed, the wormhole effects encode spectral correlations. That was a slogan. And without further ado, here's the answer. It grows linearly until the Heisenberg time, and then it saturates, exactly agreeing with what was expected from complexity. Okay, I'll skip this. So how do we understand this from the Hilbert space point of view? We both want to understand and go beyond the Euclidean calculation. The idea is that the semi-classical space of states won't be modified, so we will be working still in this length basis. But it's instead, so the state space is the same, but the Hilbert space comes also with an inner product. And it's the inner product where we will put in all the non-trivial topology changing processes. So indeed, the energy eigenstate wave functions, we take them to be unchanged. It's the same thing as if we were computing for half disks. And these functions are explicitly known, but we don't need them for this talk. So how do we get but what we will see is that these different states in this vector space are not orthogonal, even though you would think that if I have a two-sided setup connected by an Einstein-Rosen bridge of different lengths, they should be orthogonal. What we are saying in the full quantum gravity theory, it's not. And how do we see that? We insert a complete set of states Okay, so one thing I didn't say, I'm sorry about that, I was rushing, is that the interpretation of this random matrix theory is that JT gravity is dual to an ensemble of quantum systems. So here I'm imagining that I'm in one member of the ensemble and I'm inserting a complete set of states. Okay, so by our assumption, I can just plug in what these wave functions are. They are real, so I don't need a star. And so this is the inner product in one member of the ensemble. Then we can take ensemble averages, both of this inner product and any moments of these inner products. And okay, so for the expectation value of this inner product is this. And we have a genus expansion for this. At genus 0, we just get the delta function. So indeed, that's the physics we started from. These are orthogonal states. But at genus 1, we get a wormhole in here. So what kind of geometries are we summing over? So we have two geodesic boundaries, L and L prime, and then we fill in whatever gravity wants to fill this in with. This thing is when it doesn't put anything in there, and then as we go to higher and higher genus, we put more and more rich stuff in between. So, okay, this might look like a made-up thing, but it's relatively easy to show that this prescription reproduces all Euclidean gravity results with any number of boundaries. And it tells us what the resolution of this non-normalizability of the density matrix is. It's simply that this was not a density matrix. It only emerges when we do the ensemble average, but we shouldn't interpret these wormholes as giving rise to a mixed state. Okay? So this inner product, I won't have time to go through this, but this inner product is degenerate. And there are many null states. We can construct these null states in any member of the ensemble, but there's not a null state that is shared between different members of the ensemble. And through explicit computation, you can show that it leads to a reduction of the dimension of the Hilbert space from infinite dimensional to e to the s dimensional, which is what we need for an object with finite entropy. Okay, let me skip this. And because we have a Hilbert space, we can now define operators acting on this Hilbert space, in particular length operator. The good thing about this is that it will have a probability interpretation which was obscured in the Euclidean view. So this is one class labeled by delta of length operators that we can define. There's an ambiguity on how we define them. But there are universal features between all of them. So let me guide you through this, and this is the last part of my talk. So we form this L cat, L bra object. Then we take the exponential of the length, but we are doing this at the operator level. Then we take the log of the operator, divide by 1 over delta. Okay, so it's a little bit of a mouthful. But note that if L's were orthogonal, then all of these definitions would reduce to this usual definition of the length. So what the exponential is doing for us is, since different L's are not necessarily orthogonal, it picks out among the L's the one that is the shortest. So that's what we want. So there's a gauge equivalence between different L's, and we want to a useful definition in order to avoid divergences is to pick the shortest one. So that's what the delta is doing. Also, if you have a superposition of geometries, this doesn't pick the shorter one. It keeps the superposition, so it's not some violent intervention. So for delta it goes to 0, we recover the Euclidean calculation. But from this point of view, it looks more natural to take delta goes to infinity, to really pick out the shortest geodesic among the equivalent ones. It's a little hard to do analytic computations with this, So in the paper, we only do numerics. Since then, we've been working on more analytic control. So this is the result. The blue curves, the dotted and the solid are the results, depending on where we put cutoffs. I mean, this is not, this is a numerical calculation, so there's some error. So the black line is the genus 0 result, and then by doing matrix model calculations, we get these curves. And indeed, this is the time when so this is saturating at the Heisenberg time. We can also consider more complicated things like the velocity of this length. So we take the commutator with the Hamiltonian corresponding to time derivative. We can ask detailed questions. What fraction of the state is growing and what fraction is decreasing? You see that initially things are growing at the speed that they should in classical gravity, and at late times instead we get a mixture of 50-50 mixture of growing and decreasing contributions, and that's why this length is saturating. Okay, so here's the summary of the talk. We were considering the path integral and Hilbert space perspectives, and how they give us complementary information, both conceptually and in computations. And I'll let you read the outlook. Thank you very much for your attention. And sorry for going over time.
Thank you. No problem. Questions?
Can you say a few words about why that operator is well defined? It's not completely obvious.
Yeah, that's a great question. So any such operator, you could choose any like Gaussian or anything like this. So you need to show that it's Hermitian and it takes null states to null states, and you can just show it for any function.
It has to be positive, definite, and bounded, right? Otherwise the log is going to diverge. What is inside the log has to be positive, definite, and bounded.
Yes, but exponential is a positive definite function.
You integrate over
yes.
Minus infinity, plus infinity. Mm-hmm.
Okay, that's a great question. Yeah, we only showed this in microcanonical windows yeah, you can see that, so these are for different cutoffs and there's no cutoff dependence, but I think we haven't shown it analytically, so that's a great question.
More questions?
The bulk of JT gravity is just fixed ADS2. And suppose I use global coordinates to foliate the geometry. Do you want to tell me that the length of space-like geodesics grows linearly with T on just fixed ADS2?
Yes, because so this weakly boundary is fluctuating. So it's fixed ADS2, but with a finite cutoff, which we take to be small, but nevertheless finite. So this includes boundary gravitons. What you're probably used to is to instead describe ADS-CFT in Pfefferman-Graham coordinates, where it's the metric that's fluctuating. But these two descriptions are equivalent. So the fluctuation of this geodesic length is coming from the fluctuation of how we cut out from a rigid ADS2 geometry where the boundary is, because the only thing we fix is the length of the boundary.
We have time for one more question, if you have Okay.
So in the analysis, it was important that you found that L prime and L on the average is not orthogonal, right? Is this somehow related with the story of Balasubramanian and company on black hole microstates and overcounting of black hole microstates?
Yes, so this is a general feature that's emerging, that different looking semi-classical states are actually not orthogonal. This was, I think, first pointed out by Jeffreys for the thermofield double, and has been used in various contexts, including the one that So for example, if you included matter, the state with one matter particle and two matter particles are not orthogonal in the full theory. And that's what resolves all, basically that's the key insight that resolves, for example, black hole information paradox.
Okay, so thanks again.